Okay. So, happy Wednesday. Hope everyone had a delightful weekend and it was restful for everyone. Over said weekend, I graded the last homework before the current assignment, and my desk is a mess. So, that's, I have too many files of papers. It's spring, it's time for spring cleaning, it's overdue for me. So, this is the most recent assignment. I'm just setting it out here so everyone can collect their paper. While grading it, it occurred to me that I was missing a few, possibly due to people being absent. I hope it's not because I've misplaced something. So if you definitely turned yours in and you don't see it up here, please do let me know. If you didn't turn it in, please do turn it in and let me know that that's why it wasn't up here. I'm not going to hold it against you. I just need to know for my record keeping and for my sanity to make sure I don't go crazy thinking I lost things. Is it more reason I thought? Okay. There is one that is nameless, whoever it was just didn't write their name on it that I can tell. So if this nameless one up here is yours, do please tell me. So during the day, please come and collect these and let me know if you turn yours in and you don't see it up here for some reason. If you didn't turn it in, please do. I still, or at least let me know if you didn't turn it in so the records can be corrected. It's not an issue on my desktop. Now, as for the present assignment, I believe I said it was due Friday, right? Okay, good. That's what I wanted it to be. I'm not crazy. Just not about that. This whole board screwed down, isn't it? Nailed it. Okay. So let's talk about upcoming calendars, such and such. Today, we are going to talk a little bit more about vectors because vector addition is weird and vectors themselves are weird. So we're going to be working on assignment number 6, assignment 6 together today. Talking about the remaining principles needed, working some more samples together. That assignment will be due Friday, April 9th. On that day, we will begin looking at the next assignment. We're going to start moving, at this point, we're moving into the material you'll be starting with in Physics 1500. So we've started talking about vectors. We're going to start looking at more formulas, doing some more algebraic work, and looking at more and more specific cases of vectors and variables that count as vectors. Eventually, we're going to get into talking about Newton's laws, which is kind of like, Newton's laws is like peak intro physics. Newton's laws is the physics people have been doing for hundreds of years. And it has a surprising amount of applications to every part of their life. So at the very least, we're going to cover that by the end of the semester. So current homework due on April 9th. That is when we'll also begin looking at the next assignment, getting into all that stuff I just mentioned. Next week will be a normal class week. The next homework assignment will be due on, I'm planning, the 16th. The week after that will be a little funky because Honors Day is the 21st. So we won't have class that day. Instead, wait, when did I try our next test?
You said the 16th or the 20th.
Okay, so I want to get one more assignment in before that test, so that'll make it the 23rd. So the next test will be the 23rd. We will begin working together on the next assignment on April the 9th. That next assignment will be due on April the 16th. Our next test will be April the 23rd, and we will spend the last week of April going over everything we've covered together to get ready for the exam. We will only actually meet once the first week of May before exams start. That'll just be more exam prep. And so, yeah, so that means that there's, including this assignment, there's this current homework assignment. There'll be one more assignment before the next test, and then we'll be moving into review time. How do you guys feel about all this information? Okay. Any questions about anything so far? Okay. Again, good short-term dates. Homework 6 due on the 9th. Homework 7 will be due on the 16th. Now, speaking of homework 6, let me. What I'd like to do today is look at a couple of needed formulas for the rest of the assignment that I may not have specifically mentioned yet, so that all the information can have been presented, and then we can spend the rest of the period just working problems together, answering any questions you have. If I can find where all my files went. They exist. My computer's just a mess. Okay. So we have been looking at vectors, one-dimensionally and two-dimensionally. We live in a three-dimensional universe, which is to say that any given point in space can be defined in terms of distance in the x-axis, x-axis, y-axis, and z-axis from some other point. And because we live in a three-dimensional universe, our vectors can face any in three directions. Sometimes they will be in one axis, sometimes they will be in many at once. For this class and all of physics 1500 and 1510, we will primarily be doing math in terms of, at most, 2 dimensions. We live in three-dimensional space, which is to say that we have x, y, and z coming out of the board, but the z-axis exponentially complicates all of the math. So we're mostly going to be focusing for this class and the next one on just 2 axes at once, at most. We are going to look at plenty of problems that are simply in one axis at a time, though. So, all vectors, given that they have to point in a direction, have to be in some axis. At least one, possibly two. And these are the main vectors we're going to be working with for now and at the start of 1500. There's 4 formulas up here, but there are 3 vectors represented. We've already used them, but I'm going to formally define them real quick. We have, represented by delta x, sometimes represented by delta y, we have vector displacement. And displacement is the vector distance and direction between 2 fixed points. So driving from wherever you were this morning to here, the displacement would be, just draw a straight line between those 2 spots on the map. What is the direction and magnitude of that line? So displacement vector only cares about start to finish, distance, direction, not like the total the entire time. Doesn't matter what route you take, the displacement is just straight line from start to finish. Most of the problems we're going to be working with will involve moving in straight lines anyway, for convenience sake. So displacement, straight line from one blank point to another. We could call this distance if it helps. Distance between 2 points. With direction. And we will tend to be measuring displacement in units of meters. Because physics likes the metric system. In Imperial in America, we like to use feet and centimeters and inches. Physics classes, you're mostly going to be working with meters. Now, the next vector of importance is velocity. And the easiest definition for velocity is speed with a direction. When you're driving a car, your speedometer doesn't care if you're going north, south, east, west. It just tells you the number of speed. So speed by itself, the number the speedometer gives you, is a scalar. It cares not for direction. Velocity, however, does care about your direction. So if you have a different instrument that says north, you can take your speedometer reading and look at the direction and figure out the actual velocity vector using those 2 pieces of information. Velocity, we like to measure it most often in meters per second because it is a measure of the distance you are traveling in some amount of time. Distance, you know what, better definition, displacement over time. In order to have a velocity, you do need to move some distance in some amount of time. If I don't move, what is my velocity? 0. No displacement, no change in distance. You plug in a 0 there, you're going to get 0 velocity. You can cover the same distance in 2 different amounts of time and have different velocities, just how fast you make that trip. And the formula for velocity helps us to remember this fact. The notes present the little vector sign under it. Out of habit, I draw it on top. They mean the same thing, it just means this is a vector. I apologize for consistency. So the first of these wonderful formulas that this department will keep calling this until the day the school closes. velocity equals change in displacement, change in your physical location, divided by how long it took for that change to happen. So the formula is the definition of the thing. That's kind of what this little, if you've ever questioned why this equal sign has an extra line in it, that means it is more powerful than just a mere equal sign. That means is defined as. So the definition of velocity is a change in this displacement over change in time. Yes?
I have a question, but it might veer off what you're talking about.
I'm fine with tangents. Please proceed.
So when doing velocity, if you do displacement over time, if you're supposed to add two different velocities together, you would do like 13 miles over half an hour, and then add the two different ones together.
That would depend a lot on the question.
Okay.
If you were talking about, say, adding velocity vectors together that weren't in the same axis, that would involve trig work.
Yeah.
So whatever A is and whatever B is, you would not add them directly together. But if for some reason you did need to take two velocities and just add them, then as long as they were in the same unit, they should just add together. As long as they were both meters per second, you can solve the fraction. You don't have to worry about fractions. You can just solve the number, like 13 over 2 plus 30 over 6. You can just reduce those and add the numbers together, as long as they're the same unit.
I was kind of basing it off number 18.
Okay.
Because it's talking about adding 16 and 17 together.
Oh, okay.
So I was confused on how to add the two velocities together if you were supposed to do displacement over time enough.
Okay, that's a great question. So 16, 17, and subsequently 18 are not actually about adding velocities. They're about finding two different displacements and then adding displacements together.
Okay.
Let me see if I can sign that up on the screen real quick. Hey, there it is. So, very good question. This is relevant to the formula we just talked about. So in number 16 and number 17, we are given a velocity. We have the magnitude, which is the speed, and we have a direction. So in 16, we have 40 miles per hour east. In 17, we have 60 miles per hour at 68 degrees north of west. I will go ahead and draw that, because this is new notation for some people. So for 16, the velocity vector, velocity is a vector, that means we can draw it with arrows, would look like this. We're just headed straight east. For 17, 68 degrees north of west. When written like this, you want to start with the second one, because we're starting we're starting west and then tilting this many degrees towards north. So we start with the west axis, draw 68 degrees in the north direction from that axis, and then that's going to be 60 miles per hour in that direction.
Do you not want us to divide the miles per hour by the hours to get the number of miles?
It won't actually be division. If we look at, I'll write the formula specifically since it's not on the screen anymore. For both of these questions, you are given a velocity and a time and asked for displacement. So this is general order of operations for any physics question where you are given physical variables and asked to solve for something. General order of operations is always look at and list what you know from the question. For both of these questions, we know velocity vector and its time, and we are asked for displacement. So we know velocity, we know time, we are asked for displacement. You take that information, you look at your formula sheet, you figure out what formula contains the things you know and the thing you want. So that's this formula for right now. And if we were to start plugging variables in, let's say we do 16 first, we're going to plug 40 miles per hour in for velocity. Delta x is our unknown, and our time is 0.3 hours. To get delta x, we're actually going to multiply both sides by 0.3. That's because this unit is miles per hour. We need to multiply miles per hour by hours to cancel hours and just get miles. And that will give us some value for delta x, probably in the ballpark of like 12 miles. Thank you very much. 12, is it exactly 12? Oh, neat. I love when variables work out evenly. Do pay attention to units. We were specifically given miles per hour and hours. Those would cancel to give us an answer in miles, which is not metric standard type, isn't type. As long as the unit is, as long as the answer is correct for the unit you write, it'll be fine. 17, we don't actually need to worry. Okay, hang on. For both questions, we are asked for vector displacement. Displacement is a vector. We care about direction. The velocity was pointing east, which means our displacement is going to be east. We were heading east. That's the direction we're moving in. So our displacement will be in the same direction. So that is the full final answer. 17 will work the same way. Not much variance there. Our velocity is 60. Solve for delta x. Our time is another 0.3 hours, actually. That would be closer to 18.
18 on the dot.
Cool. I'm better at mental math than I give myself credit for. This is going to go to my head quickly. So, solve for the variable, that'll tell us 18 miles, and this will inherit the direction of the velocity again, so the direction on the answer would still be 68 degrees north of west. Why do I do it? Why do I step on things? So, for 17, 16, and 17, we've solved for two separate displacement vectors. 18, well, 18 is kind of listed here twice by accident. This one's supposed to be 19, but they both call back to 17 and 16 anyway, so just I apologize for the awkwardness there. For both of these, we are asked to take these two displacements and add them together, like in previous parts of the assignment. So we now have these two new vectors. For number 18, we are going to draw those two vectors tip to tail and show physically what they would look like added together. To give a quick sample of that. And they do not need to be exactly to scale since this is a 10 by 10 graph functionally. But if we were going 12 miles per hour straight east, followed by 18 miles at this angle, this will not be perfectly to scale. It would look something like this. We go east, we turn, now we're going in that other direction.
Is that the graphical answer, or do you triangle?
This is the graphical answer. The graphical answer is to help set up the mathematical answer. Well, okay. One thing to add though is This is the graphical representation of the final vector. This is the thing that we are adding them together in order to create. It's the red line labeled C. So for 18, this is the solution. And this will assist in the mathematical version of the problem, because pictures are always handy when dealing with vectors. For the second 18, the one that's supposed to be 19, we're going to add these vectors up the mathematical way, which will entail breaking them up into their x, y components, adding x to x, adding y to y. Thankfully, the answer to 16 is already entirely in the x-axis. So that one doesn't actually need to have any trig done to it. Its y component is 0. As for 17, its components will need to be broken up into pieces, trigonometrically speaking.
Can you repeat the steps you did for
Oh, yes. So, in order to add vectors mathematically, you can only add x components together, and you can only add y components together. So we need to look at each vector's x component separately and its y component separately. 16 is convenient because it is, the original vector was 40 miles per hour east. The displacement we solved was 12 miles east. East is just straight due east is the x-axis. So the vector form, like the coordinate form of this vector would just be 12, 0. There's no y component. 17 will take just a little bit of work. But for this triangle, we do already know one of the non-right angles and the hypotenuse. Nope, I should be doing these x and y. We can use just a little bit of trig to divide this up into its x, y components, and we can write 17 in coordinate form, add x to x and add y to y. Yes?
Wouldn't we know x too? Because it's the 12 miles from 16.
17 itself is a separate vector. Like, after we do 12, we are then going to go back, we are then going to completely switch gears and go the direction of 17. So, if we were doing one right after the other, are you saying we should know this is 12?
Yeah.
Let me check something just really quick. Okay. When looking at the vector presented from 17, its x component is not actually 12.
Okay.
I didn't draw the picture to scale.
Yeah.
I apologize.
No, that's fine.
The scale picture, I should have thought about this a little more. The actual to scale picture would look something a little more like this. So we do 12 miles due east. We're then going to turn and do 18 miles in this different direction. So one right after the other. We do know this angle. And this is not a right triangle if we were to draw in the third side. So for the first leg, we go entirely x-axis, forward to the x-axis. For the 17 leg, we are going to go north and then backtrack west at the same time. So we do need to find this piece here because it's working against the original 12 miles east.
Okay. I get it.
Does that help?
Yep.
Okay. Oh, got the two velocities of the car. Oh. I see what you're asking about now. I didn't read my own assignment, and I apologize. This 18 is about adding displacements. This is the picture for 18, that's the end of the question. This 18 was about velocities, and I didn't read my own question. I'm sorry. Thankfully, I can fix it very quickly. Because, like you can draw a displacement triangle, you can draw a triangle out of any vector, even if it's not one you could physically see in the real world. You could see someone move these distances and you would see this triangle. But you can do this with any vector, not just the visible ones. Force is a good example. If someone pushes to the right, pushes a box to the right while someone else pushes up at the same time, the net force is going to point that way and the box will go that way. And you can represent that adding the vectors together using trig. So we are going to, instead of adding vector displacements, we're going to add vector velocities. I can change this very quickly. For 16, the velocity vector was 40 miles per hour east. So the vector component, the coordinate component of that would just be 40, 0. That principle still applies. But the units are now miles per hour. For 17, we did 60 miles per hour in this direction. So we'll use that as the hypotenuse instead. Break that down into its vector components. Which I'm getting as the x-axis. Wait, what? Oh, I did sine. No wonder. That is what I'm getting for those two sides. So, those are the two vectors that we are adding together. It represents the two velocities we are adding. Since there are different axes, we can only add their like components together. Yes?
Why is the bottom arrow going to the left and not to the right?
This
I see what you
is
did.
just
Yeah.
the 60 mile per hour piece. If I were to draw the full triangle in real quick, drawing them tip to tail, the first vector would be the 40 this way, then from that point, we do the 60 that way.
So we always draw the arrows going in the direction of the
Correct.
if it was going like this, then it would be like this. So then the X would have been positive if it was facing forward.
Correct. For the 60-mile-per-hour leg of the trip, we know that for this particular vector, we are at this angle north of west. So we start west, we tilt north, we're moving in that direction, so we're going north and west at the same time. That means the X piece has to point up north, and the Y piece has to point up north, and the X piece has to point negative west. Which is the reason why I've written the X component of 17 as a negative number is working against the positive number from part 60. Yes?
So you didn't have to do that with 16 because it gave us just a straight line.
Correct. It gave us a primary axis in one dimension, no variation. So it already came packaged in this type of form.
So then do we just like add those two together?
Yes. Now that we've got them separated, we can add the x's and add the y's to create the final result of, that would be 17.5, I think, in the x, and then 55.6 in the y. Is that right? Okay. So, this combined velocity vector, bless you, this is what would happen if we were doing both of these things at the same time. Say the car is trying to drive in this direction, but there's a really powerful wind blowing in this direction. Both would be applied to the car at the same time, and as a result, this would be how fast the car is moving. It would, every single hour, move this many miles east and this many miles north. This, written as it is, acceptable answer to this question. This represents the vector sum of those two velocities. What 20 is asking is, the velocity found in this question, this is supposed to be number 19, how far would the car drive in 0.3 hours? How does this compare? And when I rewrote this assignment, I didn't rewrite this part even though I had to. Things slip through my drafts. Right now, the period is ending. I don't have a good way to rephrase this quickly. Let's just mix this one for right now. Because the way that we've been doing the graphical ones, we didn't find a number for it. And I don't like the way that it's worded. I don't like the way that I left it worded. 21 is still a good question, though. Can we add a displacement and a velocity together? Really? Correct. Good. Displacement and velocity are two different vectors, technically speaking. They are related vectors, but they are different. For kind of an extreme example, can you add a distance to a force? They measure completely different things. It would be similar to trying to add degrees Celsius to pounds. They are technically completely separate measures no matter how related they are. So that is your official answer to number 21. We're skipping 20. The rest on this page are good examples of specific vectors. And let us, yes.
Do you want us to explain in detail in 21?
More detail is appreciated. In general, more detail is better than not enough. That said, I'm not expecting a full thesis statement. So don't break your hand. Include as much detail as you think would be helpful.
Can you, the vector triangles for either 12 or 13? You see how you set up the triangle?
Yes, yes, I can do that. The way that they are written, like the order in which they are written, is the key for how to draw them. So,
I don't got the triangle drawn, I don't think my vector triangle. I don't know how the angles in my vector triangle. I don't know how to do it.
where's my line eraser that I need more of? I don't have. This will work. I miss when I was the only person lecturing in this room. So for 12, for number 12, we are starting with B and then we are subtracting A. So for B, to start with B, that's 6 miles at 124 degrees. So from the origin, starting on the x-axis, we go 120 degrees counterclockwise from there. I'm sorry, 124 degrees. And so B would begin in this direction. Equals 6 miles. Then we're subtracting A from B. So from B's, we now need to start drawing A's tail. A, under normal circumstances, is 4 miles at 30 degrees. So draw a new origin right here. You see where 30 degrees should point from that position. But we're subtracting A, so we need to reverse that direction. Correct. So A would actually point 4 miles in this direction. So that would end up being 30 degrees from the negative x-axis. So, to numerically add them together, each of these two vectors needs to be divided up into its component legs. Add the x, add the y, and the final vector should point this way.
I had the 30 on both sides.
These are hard to picture, which is why for the rest of this class and for the next class semester, I'm going to try to include more pictures to begin with.
And so what angle would you use for the triangle with the 6 miles?
Great question. So this is 124 degrees from the x-axis. The vertical axis is 90 degrees from there. So I would redefine just the piece inside the triangle as 56. No. 124 minus 90 is what? I'm doing the math. My math brain is failing me. I have 34. I'll draw B very quickly. Sorry, 13. 13 is very similar, but we're starting with A and we're multiplying a few things. So A, 1 to 30 degrees. 2 times 4 is 8, so that hypotenuse has a length of 8 at 30 degrees from the x-axis. Then, at the end of A, at 2A, we are subtracting through B. Drawing new little baby origin. B would normally point in this direction, 124 degrees. Instead, we're going to be pointing at 3 times B in the opposite direction. 3 times 6 is 18. And help out a little bit. Negative B is the opposite of positive B. And since we defined positive B from the positive x-axis, all we need is this little piece right here to sort of draw our triangle legs. And I'll go ahead and give you that one. 180 minus 124 is 56 degrees.
So the other one, where you draw a triangle over there, would that be 60 because of the 90 minus 30?
Yes, if you drew the other triangle like this, this would be 60 degrees. And the ultimate final answer, the vector sum for 13 should look like that. Something like that. Okay. This will be due by the end of our next class meeting. So we'll open up and answer any lingering questions that you guys still have about it. Do be working on it the next couple of days, and do please send me any questions you have. Please do it. Please send me questions as you're working. Email me, find me, whatever works for you. We'll meet back up Friday. We'll collect this, and we will begin looking at sort of the next step when it comes to how to do all of that. So you have an excellent day. Healthy. Love the day inside. I hope that holds. I'm just rambling this time. You guys can go. I'm just talking to the air. Do collect your old homeworks, please. The most recent assignment is up there for you. Collect them, fidget study aids. If you don't see yours, please let me know.